Yeah, I'm pretty excited to be here because I'm not a scientist. I'm actually practically a miner that goes around and hack bombs on slopes. So it's just great to come here and listen to all the great talks and talk to people. What?
How long did you ski patrol?
Patrolled 7 years in Copper Mountain and another 4 years in Manhattan, New Zealand, before I came here. And are we on?
Yeah.
So I changed the title a little bit just in case the folks at the mine will actually ask to see the presentation. Alec is a co-author on this presentation because a lot of stuff came from Alec and we worked a lot of stuff together on it. And might as well start. Okay, so a little bit about my background. So I came from Juneau. And by now you probably realize I'm not originally from Alaska. In fact, I'm from Israel. And occasionally we do, I was born and raised in Israel, and that's where I lived most of my life. And occasionally we do get a little bit of snow in Israel, but overall the amounts of snow are very, very small. When you Google Israel snowstorm, this is what you get. And just to give you guys an idea, what it says here, the word is sheleg, which is the Hebrew word for snow, just so you know. And as you probably know, we have a lot of problems in Israel, but let me assure you, none of them involved snow avalanche. About 11 years ago, I moved to Colorado, and the avalanche scene in Colorado, very different. But I felt like as a ski patroller, I can basically blast my way out of most of avalanche problems. And it feels pretty comfortable. It's a pretty comfortable feeling. And then I remember in 2008 in ISSW, I was sitting and listening to Blaze talking about glide avalanche in the Road to the Sun project. And I look at the guy and I can see the pain in his face. And I'm thinking to myself, that's interesting. I'm never going to deal with that stuff. Good for me. And then 4 years ago, I got a job in the Kensington mine in Southeast Alaska. And this is what I ran into. Glide avalanches. And yeah, they sounded pretty big. And so basically this story is, I tried to figure out what's going on. And 2008, 2009, we have 4 different cycles of glide avalanches throughout this season. Collected a lot of data, went to Carl and say, help me up here. Let's sort it out, see what we can get out of it. So we came up with a few nice charts, and I'm not going to explain to you guys anything because what we find out that none of those environmental changes like temperature, rain, precipitation, even stream flow help us forecast anything. It seems like just traditional forecasting methods not going to help us out. It just seems as challenging. So basically my presentation is going to be a story of desperation in some way. So what are we going to talk about? Actually, glide avalanches are not the only avalanches we have issue with. And in general, we have problem researching natural avalanches. The reason for that is we rely mostly on personal observation. And that's, usually it's once or twice a day, someone driving down the road and looking for avalanches. So we don't know exactly when they happen. It's pretty confined to area we can actually access easily. And we have a natural bias for large avalanches. So what are they going to talk about? They're going to talk about, just in general, time-lapse photography, how it works, and what we need to make it happen. A few examples. They're going to talk about measuring glide rates. That helped me a little bit. The timing of wet slab avalanches, rain or snow event, Cornice fall, and then at the end, I'm just going to put a little bit pitch of something else I do, and hopefully I'll be able to get some information from you guys. So this is how Wikipedia basically describe glide avalanche. Doug, that's videos for you.
At least I hope not.
Just so you know. For the purpose of this talk, it's going to be basically time-lapse photography is a series of photos that have been taken in set time interval from a fixed place into the same direction. And what do we need? We don't need a lot. Basically, we need a time-lapse camera, power supply, and a mount to mount it on. And this is basically what I have at the mind. I started with those funky-looking old point-and-shoot Canon that we modified a little bit. Now I have a little nicer cameras with just a small solar panel. Just keep on feeding it, and I just put it on trees all over the place. And they're just shooting cameras, and I can come and download whenever I want to. So the first example is going to be glide avalanche, and that's from the mine where I work. It's in Southeast Alaska, coastal climate, lots of precipitation from all kinds, and the snowpack is generally speaking fairly warm. We have two slopes that affect infrastructure that virtually producing glide avalanches fairly constantly every year, and we have fairly documented glide avalanche activity on those slopes. And these slopes are pretty steep. They are 45 to 55 degrees, the start zone. It's about 3 to 800 meters above sea level, so not very high elevation. And the bed surface are usually elder trees and rock slabs. So we have camera. What we use is simple methods of pixel counting. We have a set area in the slope where we just go and scan every picture and count how many dark pixels we have. The increasing number of dark pixels basically indicate that those glide cracks are increasing in size, and we're measuring the rate of increase in size. And this is what it looks like. This is a span of about 4 hours during April 28, 2011. You guys want to see it again, or?
Yeah. What was the weather leading up to that?
That was just a nice spring day. But I've seen it where it's well below zero, overcast, raining, snowing. Yep. So when we look at changes in the number of dark pixels over time, we see almost exponential like increase in the rate of dark pixel. And for me, as an operation, when I start seeing start the increasing trend start to go up during the day, that's when I know I need to start making phone calls and close areas. So that being said, we have quite a few examples of increasing glide rates, and then it stops. And then it starts again maybe the next day, a few days later, and then it stops, and sometimes it's just stops till the end of the season. Second example is wet avalanches cycle that was again in Davos, eastern Swiss Alps. And during we took the pictures just across from Alex's window every 5 minutes. Alex took pictures. So this is what it looked like. From February 28th till March 13, Alex actually managed to capture about 56 different avalanches. So what's nice about time-lapse photography, you can you basically relate all those avalanches to exactly when they happen during the day. And we try to compare it to weather changes throughout that period. And obviously we see the diurnal change when we're looking at it, and we compare it to air temperature. It's not really clear. Some of them happen below freezing temperature. Some of them happen as temperature going up, some of them as temperature actually decreasing. We don't really see any obvious trend here. The same with net radiation. Sometimes it's in positive net radiation, sometimes it's in negative. We didn't really see any clear picture. When the ALEC actually compares to surface temperature, we actually see a lag of about 5 hours from the starting of increase of surface temperature till we start seeing avalanche. And then we see some sort of lags after 4 days of avalanche cycle, and then it picks up again. The third example is from rain or snow event. You guys probably all aware about the big avalanches that blocked the road, the Richardson Highway to Haines in January. So we have a mini event like that around the mine. So looking at the January precipitation, we had about 1.5 meters of snow in the start zone at the beginning of January, and we start getting some sort of a mixed bag of rain snow event at the beginning of January, but overall it seems fairly promising. On the 13th, we have a warm front coming in, and at night over the 13th, it's turning to rain, a lot of rain. We got just over 50 millimeters, or just 2 inches of rain in less than 12 hours. So, yeah. So, well, you know, I'm from Israel, and we usually don't do rain, but I don't made out of sugar, so we decided might as well go and check out what's going on and go and start flashing snow of the start zone before the rain water gets too deep. So we're heading up basically at 9, which is about the time we start having light, and we go on this road, which is basically a channel of slash. As we're going up, we see trees that basically collapse under the weight that we didn't see the day before. So it was pretty obvious that nature is up to no good here. As we're getting up higher, we start seeing 20 to 40 centimeter deep rain-triggered avalanches. Looking a little closer, it seems like it's pretty obvious those avalanches happened quite a few millimeters of rain before we showed up. But we're still going, and then we're miners, so we're throwing bombs all over the place and try to trigger avalanches. And all of a sudden, we hear those just sound like really long, loud thunder down the valley. And we're looking at each other, and I was like, I hope we didn't bury the mine. And as it turned up, we didn't. We go down, and looking at my time-lapse camera, I just have a few just on magnets I can put on the walls on the building. Most of them kind of still buildings. So I see those avalanche here and avalanche here, and that's I can see it on my 1145 image. And it's kind of hard to see what I'm talking about. So this is what it looked like in good weather a couple weeks later. And to put you guys in perspective, yep. That person sits here on the very tip that just crossed the creek. It's about 3 meter or 10 feet deep debris. So it's fairly big, substantial avalanche. And then I went through my time lapse and tried to see when those avalanches happen and try to correlate it to rainfall. And unfortunately, all those small avalanches happen during the nighttime. So I don't have any images. I'm very interested to know how much it took to get those avalanches to go, but I have no idea. Well, as far as operation, I'm a lot more interested in these avalanches, in those big ones that can actually run through trees and reach the operation and cause damage to people and property. And they happen after between 46 and 45 millimeters of rain in less than 12 hours. So I'm not going to hang my hat over it. You know, it's just one data point, but it's good to have some sort of idea of what's going on, how much it takes, and something to start thinking about. And the last example of using time-lapse photography is Cornice fall. Again, picture are from Alec. They from spring of 2010. He put a camera every 15 minutes in a weather station, looking at this Cornice. On the April, I think it was June, sorry, excuse me. We had, he basically recorded two avalanches, two Cornice fall avalanches, and where we with June 11 and June 26. When we tried to look at what were the changes in the snowpack and weather, he correlated it to basically snow melt, which makes sense in the spring. Most avalanches fall due to deformation, we think, and it's correlated with snow melt. The first one we see during snow melt, and June 26th, they didn't have snow around that weather station. But we also see a pretty obvious trend of snow melt throughout the whole month. So it doesn't tell us much. The same with air temperature. We're seeing it's happen during the day, but it doesn't really help us as far as forecasting, and the same with net radiation. And then what we did, we actually tried to measure deformation or the strain on those cornices, what happened during that time before. And just to give you guys an idea, put together that little time-lapse movie of the cornice from the 26th. And then I basically measure the distance in between those two arrows on this slide. This is what it looks like. And it's the red line, actually the formation of those cornices that eventually collapse. And it's not a surprise. It shouldn't surprise us. What surprised me when I looked at it, I measured the formation just a few meters away on chunks that actually didn't fail. And this is what you see. At some point, you see the deformation increase much faster. That leads to the avalanche, to the Cornice fall on both sides. And obviously, one of them is nicer than the other, just cloud cover and stuff like that kind of interfere with my measurements. Maybe I'm not that a great programmer as I would like to be. So in conclusion, it's promising results as far as I'm concerned. It gave me something, just something to help me forecast. It's safe, it's cheap. Those cameras are not expensive. You can go very expensive, but you can go pretty cheap. It's powerful observation tool, educational tool. If you have management, you need to convince, they need to put money into your program. That helps a lot. Non-intrusive, and we can monitor quite a few paths with just one camera. So I think it can be used to help forecasting. It's never going to be replaced forecasting, but it could be a useful tool. But it has some issues. It's new technology, so everything needs to be done by whoever using it right now. And, as a good idea as I would like to think it is, I live in Southeast Alaska, and most of the time the view and mine is a view of fog. And this is what it looks like. It's pretty hard to do any analysis on video like this. When we try to do it, this is what you get, which is a mess. There's not much you can do as far as to use it. In the next few slides, I'm going to talk about something I just kind of started to muck around a few weeks ago. And the reason I talked to you guys about it, it's not because I have a lot to say about it, just because I hope to get some data and help from you guys, and maybe it's a little bit interesting. So I was sitting and working on a presentation for the mine, and I'm going through this video, and then I was thinking to myself, well, video I can measure time, and I can tell exactly when I initiate a fracture and when I see the parameters of the avalanche actually forming, the crown wall and the stanch wall. And if we're going to use that to measure it, from the time initiation or when the blast went off, till the time I seen the stanch wall and the crown appear, I can have estimate of minimum speed, fracture speed. And then, so I measured that and went to measure distances. And I got a picture, another video from Colorado. That's avalanche that triggered this year. So you start seeing.
Oh man.
Yeah, they're getting pretty excited. Probably should mute it. So I measured the time and the distances, and what's interesting here, and was interesting actually in a previous video, I see the stack wall actually appearing at the same time or slightly before the crown, which kind of surprised me because if I remember anything I read before, it was supposed to be the other way. So what did I get? I get some numbers all over the place, and really I need to look a little harder into it and spend more time. And it seems to me that the speed is in between 168 and 16 meter per second. And just to give you guys an idea, Jason and Bruce, they measure in 2000 and 2004 they measure a speed of warmth of a person walking with a snowshoe across a meadow. It was 20 meter per second plus minus 2. McClung was estimating 29 to 41 meter per second on a pretty dense slab. And there's, I think, Arctic measurements from the Arctics closer to 300. So it's somewhere in the middle. And it seems like the denser slab seems to propagate a little faster, but it just kind of started to muck around with it, so don't have too much data. And then again, this is a maximum speed. It's not the exact speed. So I wanted to show you guys because I'm hoping that some of you guys have videos of avalanche control that would be willing to share with me. So I have more observation. That's it. I just want to thank quite a few people. American Avalanche Association helped me with a few time-lapse camera a couple years ago. Carl Bertram was involved in it in some way or other, and we talked about it a lot. A few people from SLF that work with time-lapse, Core Alaska, some video I got from other people, and my wife that putting up with me doing that stuff. Thank you.